Today we're going to be talking about applications of the definite integral. And College Board loves these types of questions, and they are almost always going to be calculator questions. So using the calculator effectively on these types of questions. So let's look at this first one. The number of daylight minutes per day, L of t at 40 degrees north latitude, is modeled by this function here. The number of days after the beginning of 2016. January 1st is t equals 1, and December 31st is t equals 3066 because it was a leap year. So which day has the most minutes of daylight? So the first thing we're going to do is enter this equation into our calculator. So you go to y equals and type the equation in, always in radians for calculus. Okay. What I'm then going to do is graph the derivative. So I'm going to go to alpha f2. We'll do the derivative. Sorry. d dx of y1 evaluated at x. And I'm only going to graph that one. I'm not actually going to graph the original one because what we're looking for is where the maximum occurs. And I know from the graph it would make sense, but I'll show you what we're doing here. So my window is going to go from 1 to 366, whatever scale. And I'm just interested in the derivative and where the derivative is 0. So I'm going to graph that. And it's going to graph slow. Okay, so here's our derivative. So if this is the graph of the derivative, that means it is increasing to this point, then it is decreasing. So this is the location of our maximum. So I'm going to calculate the 0. So it's going to want a right bound, left bound, and a guess. So at 171.5, okay, is going to be our maximum because, justify our answer, f prime, I guess L prime of t switches from positive to negative. Now in the next question it says evaluate the integral from 1 to 366 of L of t. So let's go ahead and do that. So in the calculator, alpha f2, we're using the integral, so fn int. We're going from 1 to 366 of y1 dx. So we get this big number. So the integral from 1 to 366 of L of t is going to be 266,978.956. And what is this? Well, if this is giving me the amount of daylight per day, this gives us the accumulation of that, the sum of that, which means this is the minutes of daylight during the year from, and this is important, t equals 1 to t equals 366, or you could say from January 1st to December 31st. Okay, next problem. An ice field is melting at the rate of m of t equals 4 minus sine t cubed acre feet per day, where t is measured in days. How many acre feet of ice field will melt from the beginning of t equals 1 to the beginning of t equals day 4, t equals 3. So what we're doing is, if this is the rate, we want to multiply that by the time. Well, in calculus, we do that with the integral. So this is going to be the integral from 0 to 3 of 4 minus sine t cubed. And again, this is the calculator doing the work for us. So we're not using this multiple times, so I'm just going to do this right here. So 0 to 3 of 4 minus sine x cubed dx. And we get 10.666, which is A. Okay, a reactor coolant tank is being filled with coolant at a rate, and again, you're going to see that rate term used a lot here, 400 times the cubic root of t gallons per hour. T is greater than 0. If the tank originally contained 200 gallons of coolant, how many gallons are in the tank after 8 hours? So we're going to have 200 plus the integral from 0 to 8 of 400 t. And again, type this in the calculator. So I type this in the calculator. Instead of the cubic root, I just did it to the 1/3 power. You can type it in as the cubic root by going to the math menu, but that's fine. Calculator's thinking, and the answer is 5,000. Okay, so here's a question from the 2011 test. A cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. The can is initially empty, and rain enters the can during a 60-day period. The height of the water in the can is modeled by the function s, where s of t is measured in millimeters, and t is measured in days for 0 to 60. The rate at which the height of the water of the can is given by s prime equals 2 sine 0.03 t plus 1.5. Okay, according to the model, what is the height of the water in the can at the end of a 60-day period? So again, it's going to be the integral. So this is going to be the integral from 0 to 60 of the rate. So we're just going to do the integral of s prime, and we're going to use this in the calculator. But again, if we look, I'm going to continue to use this equation multiple times. So whether I'm graphing it or not, I'm going to put it into my y equals. So y1 okay, so there's our equation, and we'll do the integral from 0 to 60 of y1 okay, and we get 171 rounded 3 decimal places, always 3 decimals unless asked otherwise in AP, 813, and this is going to be millimeters. So if it's going at this rate, we add up the rate times the time, which in calculus is the integral. According to the model, what is the average rate of change in the height of the water over the can over the 60-day period? Show the computations that lead you to your answer. Okay, so average rate of change is going to be s of 60 minus s of 0 over 60 minus 0. Okay, we don't have s. Okay, this is slope. Okay, so average rate of change, like I said, is slope. So we're doing this calculation, but we don't have s, but we have s prime. So to get s, we need to integrate. So we're going to integrate for 60 from 0 to 60 s prime of t, which we already know. We already evaluated that, minus the integral from 0 to 0 s prime of t. Now as I'm writing this, We probably could have done this without the integrals because we know the amount at 60 is 171 and we know the amount at 0 is 0. So this is really just 171.813 divided by 60, which is approximately 2.864, the units. So looking at the units, it's the units of the top over the units on the bottom. The units on the top are the height, which is millimeters. The units on the bottom is time, which is days. So this is millimeters per day. Okay, and then assuming that no evaporation occurs, at what rate is the volume of the can changing at time 7? So let's start with volume. Volume of a can is pi r squared h. The radius of this can is 100. Is 10, sorry. Squared is 100, I'm thinking ahead. So this is going to be 100 pi h. Okay, rate is kind of a clue that we're looking for a related rate problem. So dV dt is going to equal 100 pi dH dt. Okay, well dH dt, the change in height, is the derivative of s. That's the same thing. Okay, and we're specifically interested in time equals 7. No, that's right here. So 100 pi times s prime of 7. Okay, and we'll use the calculator again. So I'm going to have 100 pi times, y1, because that's our derivative, evaluated at 7. Gives us 602.218. Okay, the units, so it's dV dt, so this is going to be the volume, which will be millimeters cubed, over our time units, which is days. Okay, part D of this problem. During the same 60-day period, rain on Monsoon Mountain accumulates in the can identical to the one in Stormville. The height of the water in the can on Monsoon Mountain is modeled by the function m, and here's m. The height is measured in millimeters, and the days again are from 0 to 60. It says let D equal m prime minus n prime. Apply the intermediate value theorem to the function D on the interval 0 to 60 to justify that there is a time where the heights of the two cans are changing at the same time. All right, there's a lot of information here. The intermediate value theorem, if you remember, says essentially if it's continuous, essentially if a function is continuous, and here's a, this is f of a, this is b, this is f of b, that every value between f of a and f of b is represented somewhere between a and c. So anything here, there's some c value that gives you any y value between here. So that's what this question is asking us. Okay. So D, we're going to look at D of 0, which is going to be m prime of 0 minus s prime of 0. Okay, I'm going to go ahead and type that second equation in. Okay. So y1 is s prime, y2 is m, Okay, so m prime. So how I'm going to type this in the calculator, and you can do this different ways. We have m, not m prime. So m prime of y2 evaluated at x at 0. And then we're going to subtract y1 at 0. Gives us negative 6.674 or 75. And I'm going to do the same thing. I'm just going to grab it and I'm going to change my values to 60 and 60. Okay, so get 69.337. So D of 60 is M prime of 60 minus S prime of 60, which according to the calculator is 69.377. Okay, we're using this to show that there is a point in time where they are changing at the same rate. So that means that M prime of 0 minus S prime of 0, if they're the same, then the difference between them would be 0. Well, by the intermediate value theorem, since negative 0.7675 is less than 0, is less than 69.377, since 0 is in between those, and this is continuous, then we are guaranteed that there is some value that it has to reach. It has to go through 0 if it's going from a negative to a positive. So by the IVT, there is some t where d of t is equal to 0. All right, so this is another problem. This is from 2012. So the temperature of the water in a tub at time t is modeled by a strictly increasing twice differentiable function w, where w is measured in degrees Fahrenheit and t is measured in minutes. At time 0, the temperature is 55. The water is heated for 30 minutes beginning at time equals 0. Values of w of t are in this chart for the first 20 minutes. So we're going to use the data in the table to estimate w prime of 12, show the computations that lead to your answer using correct units, interpret the meaning of your answer in the context of the problem. All right, so w prime of 12, since we don't have an equation, we're going to use this and that. Okay, so we're going to have w of 15 minus w of 9 over 15 minus 9. So the derivative is always just slope. We're approximating the slope at 12 using these points that are close. So this is going to be 67.9 minus 61.8 over 15 minus 9. Now here's the icky part for any math teacher. AP counts this as a correct answer to this problem. So even though it hurts my math heart, you would leave your answer just like this, because if all of a sudden you did 15 minus 9 is 7, and you got that part wrong, then you're going to get that question wrong even though you know how to do it. So you'd leave it like this. The units on the top are degrees Fahrenheit. The units on the bottom are minutes. So this is degrees Fahrenheit per minute, using correct interpretation. Now I will go ahead and, this is 1.017 degrees Fahrenheit per minute. So in this problem, the temperature is increasing at a rate of 1.017 degrees Fahrenheit per minute at t equals 12. Okay, now we're going to use the data in the table to evaluate the integral from 0 to 20 of w prime of t. Using correct units, interpret the meaning of w prime in the context of this problem. We don't have the derivative, we have the function. But thinking about the fundamental theorem of calculus says that the integral from the definite integral is going to be the antiderivative evaluated from 20 to 0. So this is going to be the antiderivative of w prime is w. So this is going to be w20 minus w of 0. Okay, which in this case is going to be 71 minus 55, which is 16. Okay, so what is this? Okay, well, we took the temperature at 20 and subtracted the temperature at 0. So this one's pretty straightforward to think about. Well, if I'm subtracting the end temperature minus the initial temperature, 16 is the increase in the temperature. So the temperature has gone up 16 degrees from t equals 0 to t equals 20. For the next one, for 0 is less than t is less than 20, the average temperature of the water in the tub is 1 over 20, 0 to 20 WT. Use a left Riemann sum with these subintervals indicated by the data in the table to approximate the average temperature. So let me explain this a little bit. So the temperature, so from 0 to 20, if I took that integral, would be the temperature over the whole time. And we're going to divide that by 20 to get the average. So this is going to be 1 over 20, the integral from 0 to 20 of w of t. Okay, they tell us how to do this. They want a left Riemann sum. So left Riemann sum, the endpoints are going to be on the left side. Okay, so the widths of our rectangles are the distance between the t's. So the width for my first rectangle is 4. The height is evaluated at the left side, which is going to be 55 for the first one. The second one, the width is going to be 5. The height is going to be 57.1. The next one's width is 6. The height is 61.8. The next width is 5, and the next height is 67.9. All of this is multiplied by 1 over 20, and I should have done that in the beginning. Doesn't really matter. And again, I'm leaving it just like that. Okay, so then it says, does the approximation, is it an overestimate or an underestimate? And the piece of this that we're going to be using is that we were told it is strictly increasing. So let's say I have a graph that's strictly increasing, and I'm evaluating my Riemann sums on the left side. Well, if it's increasing, there's area that's not accounted for. So we're approximating the area under this curve, but these rectangles are all going to follow below. So this is going to be an underestimate. Since w of t is increasing, because it's increasing, and we're using a left Riemann sum. Okay, so for 20 to 25, the function w that models the water's temperature has a first derivative given by 0.4 root t cosine 0.06 t. Based on the model, what is the temperature at 25? So what we're going to do is we're going to take the temperature at 20, and then we're going to add the amount that it's increased from 20 to 25, which is going to be the integral from 20 to 25 of w prime of t. So my temperature at 20 was 71. The integral here, so let's use the calculator. Okay, we have the integral from 20 to 25 of 0.4 root x root x cosine 0.06 x dx. So you get 2.043. So this is going to be, the temperature is 73.043 degrees Fahrenheit. Okay, a particle moves along the x-axis so that at any time t, its velocity is given by cosine 2 minus t squared. The position of the particle is 3 at t equals 0. We want to know the position of the particle at t equals 4. Okay, well, the integral from 0 to 4 of v of t is going to equal the antiderivative of velocity is position. So this is going to equal the position at 4 minus the position at 0. We know two of these. This I can evaluate using the calculator, and we know this. So x of 4 is going to equal the initial position, 3, plus the integral from 0 to 4 of v of t. Okay, so we'll type that in the calculator. Okay, so we get an answer of 3.42. Okay, what is the position of the particle when the velocity first equals 0? So we need to find the time when the velocity is equal to 0. Well, let's go ahead and plug this in the calculator. Maybe we should have done this from the beginning, but that's okay. Okay. Okay, my window, we're starting at 0. Let's go to, I don't know, 10. We can guess there. And we're really just interested in where it's 0. So if I go ahead and graph it, we're going to find it's 0 at a lot of places, but we just care about the first one. So we're going to calculate the 0. So here, guess. Okay. So according to the calculator, when t equals 0.6551364, the velocity is 0. We want to know the position at 0. So this is going to be 51364 is going to equal 3 plus the integral from 0 to 0.6551364 of our velocity. Okay, so we type that in the calculator and get 2.816. Another problem from 2012. So particle is moving around the curve, so its position, x of t, y of t, At t equals 0, the particle's position is 1, 5. That's important. And we have the equations for dx dt and dy dt. Is the horizontal movement of the particle to the left or to the right at t equals 2? Explain your answer. Then we're going to find the slope. So the first thing I'm going to do is I'm going to enter these two equations. I'm going to put this one in y1, and I'm going to put this one in y2. So I've entered the two equations into the calculator, and we will use it to answer two things. So first is the horizontal movement to the x or to the right. So we're going to look at dx dt evaluated at t equals 2. So this is simply just going to be y1 evaluated at 2, which is 0.271, which means it's greater than 0, so it's moving to the right, because dx dt is greater than 0. Then for the slope, we're looking at dy dt over dx dt, because slope is always dy dx. Just here, we get it this way. Again, we're going to use the calculator. So I just want y2 evaluated at 2 divided by y1 evaluated at 2. We get 3.055. Okay, find the x-coordinate of the particle's position at time equals 4. So this one, you're always going to be given some initial condition, in this case at time equals 2. So the integral from 2 to 4 of dx dt is going to equal my position at 4 minus my position at 2. So the antiderivative of dx is x. This we're going to get in the calculator. We know this, so x of 4 is going to be x of 2, which we know is 1, plus the integral from 2 to 4 of dx dt, and then we'll type this in the calculator. So we have 1 plus the integral from 2 to 4 of y1, because that's where we stored the dx dt, gives me 1.253. Okay. Speed. We did speed a while ago for parametric equations. Speed is equal to the square root of dx dt squared plus dy dt squared. So in this case, we're going to evaluate these at 4. So this is going to be the square root of dx dt evaluated at t equals 4 squared plus dy dt evaluated at t equals 4 squared. And then we're just going to type that in the calculator. So using good parentheses, you get a speed of 0.575. Okay, this last problem, I'm going to introduce a new equation to you, the distance in parametric. So the distance would be the integral from a to b, which is 2 times, of base the speed. Okay, so we'll type this in the calculator. So for this problem, our a and b are going to be 2 and 4. So type that in. Okay, so it's thinking. Our answer is 0.651. Okay, so these are a variety of different ways that we can use integrals in application problems.